Okay, no doubts, I suppose. Uh, any doubts, Tushar, Piyush, Vanshali? You can type it out in the chat box if you want to, in case of any doubts. And if you can move forward, just write a +1 so that I know that you are on the same page. Okay, great. Others, do you also have any doubts? Okay, great. I hope you guys are okay. Sure, sure, Vignesh. Let me know if you have any doubts, Vignesh. Otherwise, these are just function calls. I've added in the chat window as well, so you can directly speed it up from there too. Okay, great. So now we are done with the remeshing. Now we are going to look at tetrahedralization. So essentially, what tetrahedralization means is that you have a given mesh surface. Right now, you have some bunny. So let's draw the bunny. I hope this looks like a bunny to you guys. Say you have a bunny mesh. So right now the mesh is essentially covering the surface only. So all these triangles are just covering the surface, and inside it is a hollow. This is always a hollow mesh. So there is no information inside. So what you can do is essentially you can fill the inside of the surface to get a solid tetrahedral volume from this surface mesh. So what is a tetrahedra? Tetrahedra is nothing but a pyramid with a triangle as a base. So these are three triangles combined to create a triangular pyramid. Oh, sorry, these are four triangles. One is the base triangle. The fourth one would be the base of this, and you stack these triangles together to create a solid object. So what you can do essentially is you can use something called as tetrahedralization to fill the surface mesh with tetrahedrons. So this will get filled inside with tetrahedrons. So let me show you some thing which would make you understand what tetrahedralization is. So this is an example of a tetrahedralization. So if you take a cow mesh and you tetrahedralize it, you'll get such solid tetrahedrons covering the entire volume of the cow. And this is a tetrahedron. So in every cube, you create a grid, you fill it with tetrahedrons, and that will give you your tetrahedralized surface. So for this one, we are going to use something called as TEDGen. So TEDGen is another library. You can essentially install TEDGen using pip. So this is the library that we are going to look into for tetrahedralization. Uh, just quickly install this library, then we'll move forward. So now there's going to be a small operation that we are going to do. What we are going to do is, we already have the bunny mesh. We are going to try to tetrahedralize it. Uh, let me check this once. so we already have one mesh. Import. So what now we are going to do is that we already have our bunny mesh, right? So now we are going to enclose it in a bounding box. So now how we are going to compute the bounding box is that we are going to take the bunny mesh and we are going to enclose it in a box, something like this. This is required because we'll need the constraints when we are doing tetrahedralization. Since we are going to fill the entire space with tetrahedrons, we would want that there should be some external boundary constraints as well with respect to which we are going to tetrahedralize. So we are going to fill it with a bunny mesh. Oh, sorry, we are going to fill it with tetrahedrons. And for this, we need to enclose it inside a box. So in order to do that, what you need to do is you need to check the bounds of the bunny. How you check the bounds of the bunny is that we have the vertices. You check the min and the max along all the coordinates. So now we are going to look at how we artificially create meshes and modify meshes as well. So I have created a vertex list V1 to V8. Why we are doing this is because we have a cube that is being enclosed, that is going to enclose the bunny mesh, the cuboid. So we have four vertices on the bottom and four vertices on the top. So, 5, 6. This will also clear your concepts about how you triangulate different surfaces. So you have a cube like this. So now on each face you are going to have two triangles. Uh, is the diagram clear to everyone? I've just drawn the triangles that we'll be obtaining on each of the faces. So we'll obtain 12 triangles because there are 6 faces and each face is being divided into 2 triangles. So now you have obtained a set of triangles as well, and now you know what indices these vertices are going to belong to. However, before we begin, we need to take a look at how we are going to keep our points. So let's take this point to be the point which has the minimum values. So this vertex would have a coordinate x min, y min, z min. So I'm taking this to be my center, and let's say I'm creating this treating this as my coordinate space. So this is my y, this is my x, and this is my z. Is this part clear? I'm just considering this in a 3D coordinate space. So this point here would be this vector x min, y min, z min, and these values will essentially come from the bunny itself. So we want to encase the bunny so that the bunny is somewhere in the center here. So we want that the box should bound the bunny. So we'll take the minimum of the vertices of the bunny, slightly increment them so that it goes beyond the bounds. It is not touching the bunny exactly. And then use them as my x min, y min, z min. Similarly, we'll take the maximum values that we get from the vertices of the bunny. So essentially, we have the bound and this coordinate here would form my front top right. So this is x max, y max, z max. Now the rest of the coordinates of the cuboid can be treated using these 6 values. Is this point clear? So for example, if we want to look at this point, so this would be x max, y max, z min, because the z coordinate is the minimum at this point. Is this point clear to all of you? Please write +1 in the chat if it is clear. Otherwise, I'll just uh, reiterate this. Okay, great. Thanks. So now you have the bounds of the box. Now, what you need to do is construct a new set of vertices, V new and F new, which will essentially contain the bunny vertices and the box vertices. Similarly, the faces will now contain the bunny faces, all the faces of the triangles in the faces, and the box faces. Is this part also clear? So now, when you go to the implementation side, now we'll walk through the implementation of this one. Aditya sir, is it fine if we uh, go beyond the time, or do we have to strictly stick to 2 hours?
No, no, no. There is no such limit. I think as far as you and the participants are enjoying, you can take your time.
Okay, sure. So what I've done is that now once I know the vertices, I can actually create my own triangle array. So I name these vertices V1 as 0, V2, V3, V4, V5, V6, and now I've created my triangles. So now I know what triangles I need to form. So my box triangles are going to be the triangles containing all these faces, contained in these faces. So like one triangle is going to be 1, 6, 2. Then another triangle is going to be 1, 6, 4. The side face, this face. Then from the front face, I get two triangles, 5, 4, 0. Another triangle, 0, 1, 4. So on and so forth. So this is simply an array of those triangles. Why I'm showing you this is so that you can understand how you can actually manipulate these meshes and create your own programmatically. So once I have done that, now I can. So I've just simply now I'm checking the bounds essentially. So I took the least value of the minimum value and then I incremented it a little bit more to go beyond the bounds of it. Similarly, you can do. So you can simply. So this is like incrementing it by 10% and so on and so forth. Now I have also created the bounding box vertices. Uh, Now these vertices are going to be nothing but these values. So these are my vertices from all the corners of the point of the cuboid. Now what I'm going to do is I'm going to use this to create a wireframe around my. So this is just for plotting purposes. You can simply ignore the wireframe for now. You can look it up later on. This is nothing but simply I'm once again stacking and incrementing the 10% of the bounding box and creating a new set of vertices and edges to create a wireframe. Note that these vertices and edges are in 2D because each of these sets are just lines, points. So once I'm done with that, now I need to create this set of vertices and faces, the V new and the F new that I talked about, by concatenating the bunny vertices and the box vertices and the bunny faces and the box faces. So V extended is the new set of list of vertices and F extended is the new set of list. So you can try it out later on. So I'll just share this code perhaps later, and maybe I'll share the link with Aditya sir, and maybe he'll forward it to all of you.
Yes, surely.
Once you do that, you'll get a bunny that is bounded by a box. So I specifically left some space in the Z so you can actually see the floor of the bunny here. But ideally, what you would want is that you would want to cover the base as well. So this is only for visualization purposes. So you can see if you plot both the V extended and the F extended, it would look something like this. The points of the bunny are also on the base and the cuboid is also there. Later on, I'll show you a tight fit box, perhaps, but there's nothing much here. So the bunny won't be visible at all. So bunny would be inside. So if you scroll a little bit and go inside, you'll see that the bunny is inside the box. Is it visible? So you can see the bunny has been enclosed inside a box. Now we are going to tetrahedralize, where my box will form the bounds and we use as constraints. So now comes TEDGen. So we created uh, F extended and V extended before. This now. So you can simply load a mesh in TEDGen using TEDGen equals to TEDGen and pass in the vertices and the faces, just like you did with LibIdeal as well, with the plot function. So similarly, you just run this and you'll get a TEDGen mesh. Why do we do a 10% increment? Okay, so why do we do a 10% increment is just a heuristic that I am taking here. You can do 20%, you can do 30%, or you can even do 1%. So the idea is that it should not essentially touch the bunny itself. So if I take the min max as the same as the bunny, the box will be touching the bunny at those points. So you need to take a step forward and push the boundaries of the box a little bit more so that you can actually fit it without touching the bunny object itself. Is it clear, Sumam?
Yes, I got it.
Okay. So you pass in the vertices and the faces to TEDGen, and then all you need to do is call this function called Tetrahedralize, and it will fill it with the tetrahedrons. So in this particular case, I'm taking some heuristics like the minimum tetrahedral angle should be 20 degrees, the minimum ratio is 1. Then Steiner left controls the number of points that you're allowing to be generated in order to create a finer tetrahedral mesh. So all these parameters, you can check the documentation if you want to, and then you can fill it up. But there is one condition for tetrahedralization, that it should be a manifold mesh. So before performing tetrahedralization, you need to call this function TEDGen.makeManifold. So as we had discussed before, this is essentially why you need a manifold mesh. So when you're performing tetrahedralization, you would not want any ambiguities like these cases. So make manifold function internally basically uses some algorithms to remove these ambiguities. Either it will delete the vertex, either it will delete the edge and create a new edge that is a manifold one, and so on and so forth. So it will clean up the mesh for you internally and create one that is a manifold mesh, and then you can perform tetrahedralization on it. So once you perform tetrahedralization, you'll get something called as the TEDGen grid. So TEDGen grid is basically a unstructured grid data structure that they use to store this tetrahedral information. If you print the grid, you'll see that how many new points it has created. The number of points have changed. The number of cells are essentially the number of tetrahedral faces that you have now, and the XYZ bounds that have been used. So this is the grid dot plot. So this is the mesh plot that we are watching here. However, we would want to see the bunny tetrahedrons. So what we are going to use is that Vista is another library that we are going to use. So I'll just show you. It is used in conjunction with TEDGen. You can install Vista from here later on. It is also a wonderful library for geometry visualization. It's basically for 3D plotting and stuff like that. So yeah. So so this is just a setting theme. Now what I'm doing is that, say I had the bunny, right? Say I want to display the tetrahedrons from the start to the midpoint of the bunny. So essentially, I want to create a mask such that it selects only the cells. So right now, these are a set of cells. Uh, think of it as a cute bunny. So, yeah, fine. So let's say I want to display only the tetrahedrons still here. So this space is entirely filled with some tetrahedrons. And these are solid tetrahedrons. So if I view it from the surface, I'm not able to see it right now. But it's a filled cross section. So if you view a cross section of the bunny, it should be filled with some solid tetrahedrons. So what we are trying to do is now we create a condition for it to create the tetrahedron. So what we are doing now is that we had enclosed it inside a box, right? So now we will use this box, we'll take the center coordinate and we'll force the restriction that everything that is to the left of this center should be displayed only and everything to the right should be discarded while visualizing. So essentially we can use this to create a mask for the entire tetrahedral volume. So this is what I'm doing. I'm calculating the bounding box, which is nothing but the mean of the points. So once I get the center of the points, I'll use this to essentially visualize my bunny mesh. So this is the bunny, and now I've taken a cross section of it, and now you can see that it is entirely filled with some solid tetrahedrons. Can you see now? Now you should be able to see the height of the triangles as well, the height of the tetrahedrons as well. So now this is a volume filled with tetrahedrons. I'll now go through do a code walkthrough. Is there anyone of you who wants to leave precisely at 4 p.m. or can we extend it beyond? Please add a +1 if we can extend it. Otherwise, I'll stick to the timings.
Aradhya, you can continue. The session is anyways being recorded. Those who wish to leave, they can anyways.
Okay, okay.
Let's not rob those who are interested. Disinterested.
Sure. So essentially what we are going to do now is now we are going to reshape the cells. So cells are essentially not reshaped currently, but we'll convert them into a set of triangles. So once you do that, now you place the condition that if the center of these cells is less than the bounding box center, so all the points that are to the left of it should be selected. So you essentially create a mask using it. Then you check which of these are returning non-zero values and you extract those cell indices and then you plot them. So this is essentially a pretty straightforward operation. You just compare the mean of those grid cells and see if they are less than the bounding box center. If yes, you select those cells, and if these cells contain some tetrahedrons, they will be displayed on the screen. In case of any doubts, just feel free to ping. Otherwise, I think we are pretty much on time. So this is another condition. So like I picked the center value to be the bounding box center value. Now you can actually check it if it's less than 0, or you can actually use some heuristics if you want to extract only some particular set of tetrahedrons. Right now in this one I've turned off the color schemes, so it's looking something like this. Otherwise, if you turn it on back, you'll see something like the previous one. However, note that the condition now has been changed. Now the condition is less than 0. So all the tetrahedrons towards the other side of the bounding box are being displayed. Similarly, you can define your own conditions depending on the kind of operation you are performing. So you can define your own heuristics and select the tetrahedrons based on that. I hope there are no doubts in this one. Say for reconstruction of an image, extract particular features. Okay. So particular features, again, like we have seen before, those features can be extracted depending on the kind of properties you want to refer to. It can be based on the kind of curvature. It can be based on the ISO value of a surface. We will look at some of these conditions now when we will talk about the sine distance fields. And based on those things, you can actually extract a particular surface from a solid volume. So you can take care of the curvature, you can pick the angle values as well. Say you want only dihedral angles that are greater than a particular value, and so on and so forth. You can pick the curvature and different other properties that you want to. So it totally depends on the kind of operation you need to perform. So, for example, yeah, we'll take a look at the example when we talk about sine distance field. So right now I took bounding box only based on the coordinates. So it was a more coordinate centric thing that I did. But you can even select them on the basis of dihedral angles. You can select the cells, then you check the dihedral angles from the cells. If they're less than a particular value, extract those cells and display them. Why this is needed is that maybe you want to further refine the dihedral volume that you have obtained, the tetrahedralized volume that you have obtained. So maybe the heuristics that we had looked here. So right now I took the dihedral angle of 20, but maybe I'm not getting a good tetrahedralization out of that. So we can perhaps, okay, uh, fine. We'll just take a look at the dihedral angle as well. So basically, a dihedral angle is the angle between two intersecting planes. So when we talk about a dihedral angle, so I'll just draw for two planes. You can extend it to a tetrahedron as well. So let's say you have two angles, two planes, sorry. So there is an angle between these planes. This angle is essentially your dihedral angle. So this is a plane alpha, this is a plane beta, and this would be a dihedral angle that is between those planes. So when I talk about tetrahedrons, so we have two triangles that are uh, connected to each other, right? So there is an angle that is between these triangles as well. Maybe from the side view it would be much more clearer. So from the side view, if you look at a tetrahedron, it would look something like this. So if you cut open a tetrahedron, you'll obtain a set of triangles. So there are angles between these as well. I hope it is clear now, in case anyone had any doubts. So yeah, there are different conditions that you can go for, and this is how you perform. It's the angle between two intersecting planes. Yeah, it's the acute angle. Now let's take a look. Now we're going to start with sine distance field. So essentially, up till now, we have seen that we created a tetrahedral solid volume from a mesh, but there is another way you can represent it using a volume. And this tutorial will actually guide you how you can actually convert from one form to another. So we looked at meshes, we know how we can draw out point clouds, but we can even draw out voxel volumes from them. Those of you who don't know voxel volumes, so voxel volumes are nothing but a regular grid, and for every point, you can have only for every voxel, you can have only a single value stored in it. So it's like a solid volume, so to say. So all these MRI volumes that we have here are like the voxel-based volume. So it's a 3D grid, say of size n cross m cross k, and each grid stores a single value. So let's say in case of MRI volume, it would be a volume of size, length into breadth into height, and at each location you are storing some intensity value. So if it's an MRI image, it would be somewhere around, if it's an 8-bit image, so it would be storing some value between 0 to 255 at each location. If you take a slice from this is nothing but your pixel image, something like and it's analogous to a pixel image, the way you store your images. So It's nothing but a array of n cross m cross the intensity value. So 0, 120, so on and so forth. If it's an 8-bit image. I hope this is clear what a voxel volume is. So from a mesh, you can even get a voxel volume. Right now you have a mesh, but essentially you could get a voxelized volume as well. So converting this into a voxel volume. And similarly, there's another representation that we talk about, which is called as a sine distance field. Okay, the bunny has become really bad. So what essentially a sine distance field tells you is that the zero level set of a sine distance field, I think you have already covered the mathematics part, so I'll just tell you directly. The zero level set should essentially represent the surface. Anything outside of it, depending on the distance, is given some positive distance value, and anything inside is given as a negative distance value. Depending on the kind of convention you want to follow, you can reverse the distances as well. It's up to you. However, this is a generic convention that we follow. So anything inside would have a value that is less than. So you are creating a scalar field essentially with assigning distance value to each coordinate. This is what we are going to do here. And how we are going to do it for a mesh is what we'll talk about. And to verify that the sine distance field is correct or not, what you can do simply is that you can pick the zero level set from the sine distance field, and it should be close enough to your surface mesh. So after sine distance field, you'll get something like this. So you'll get uh, recursive bunnies of different scalar values. So this is something what a sine distance field would look like to you if you view a cross section of it. Note that this field is in 3D. We are only viewing it in 2D, so it looks something like a heat map. So if you look at this, so this is something what a sine distance field would look like, given that these are the polylines that are consisting the shape. I hope this is clear to everyone. So the zero level set is on the boundaries, and anything beyond is given a distance with some sign convention, and anything inside is given a distance with some sign convention. Now, how we are going to do it for an arbitrary mesh is the question. So Igl has a function called as Igl Sine Distance. Whenever you calculate a distance from a mesh, you always do it from a query point. So let's say you had this mesh. Now what you do is you distribute this, you assume a grid around this bunny mesh, a grid of points, a regular grid of points, and then from each grid point, you're going to calculate the distance to the bunny mesh. You place this mesh inside a grid and compute the points and the distances, and then that is how you're going. Because see, a bunny mesh, this bunny mesh is currently in a continuous space, so you need to perform some sort of discretization of it. So you create a regular grid around it, and then you compute the distance from the bunny for each and every point. The minimum distance from the bunny would give you a sine distance field. Note that this has to be minimum distance. There are different algorithms that are used to calculate sine distance. I hope they have already been covered in the lectures. Otherwise, you can look it up yourself as well. So you can create pseudo normals to the surface of the mesh and use that as a distance from the mesh and assign that value. And there are different other operations as well that you can use. However, now we need to see how we are going to create this grid.